Good. We are good.
Oh, cool. Okay, thank you. So hello, everyone. The work I'm presenting today is part of my research on long run-out landslide in the solar system, which I started during my PhD at University College London, and I'm currently continuing at the Natural History Museum still in London. So we run some friction experiments on anorthosite bearing gouges because we wanted to address the origin of the high mobility of the light mantle avalanche. Next slide, please. So the light mantle avalanche extends for about 5 kilometers over the subhorizontal valley floors of Taurus Littrow Valley. It originated from the submassif and likely from the summit of the submassif, although we don't really have a clear headscarp, but we have some features, some structures that may suggest that that is the source or origin of the light mantle material. Next slide, please. So in the literature, we can gather some proposed mechanism to explain the high mobility of the light mantle. We have the gas fluidization by solar wind volatiles by Schmidt et al. 2017. Another 2017 paper by Kokelar et al. Looking at lunar granular flow, suggested regular entrainment. And then we have some other mechanism like the dry fluidization by dynamic fragmentation, where the fluidization is driven by the finer fraction of the debris, and then the theoretically available acoustic fluidization. But some of these mechanisms are difficult to prove because of lack of theoretical and experimental support, and obviously in this case the scarcity of field data. And we know how important are direct observation of the internal structures of landslide in general to gain insight into the mechanism of emplacement for terrestrial long run-out landslide. Next slide, please. But regardless of the emplacement mechanism, it is thought that the localized shear stress to a narrow slip zone lead to the development of high frictional heating that then triggers a series of chemical and physical reaction that are then responsible for the development of friction weakening mechanism. And so at the beginning, we have the acceleration that is driven by gravity. And then it is further promoted and rapidly promoted by a series of velocity weakening mechanism that also lead to strength loss and to the development of high velocity already early in the early stages of this catastrophic mass wasting event. Next slide, please. And so some experimental work has been used to investigate this friction weakening mechanism in terrestrial long run-out landslide. However, none of this work has been done in extraterrestrial analog material to investigate the availability of this type of mechanism in extraterrestrial environment. Next slide, please. And so that's what we decided to do, to investigate the viability of dynamic weakening mechanism in anorthosite bearing gouges. So anorthosite bearing material would represent an analog for the submassif forming material, although we are learning that the lithological composition of the submassif is far from being so simple. Anyway, we requested anorthosite bearing rock to the ESA sample analog curation facility. And we then run some friction experiments with Shiva, slow to high rotary shear apparatus at the National Institute of Geophysics and Volcanology in Rome. So we grinded our rock, and we to obtain a gouge and put in a sample holder, which is then put in the sample chamber. So from one side we have a stationary loading system. From the other side we have a rotary column, so that we can generate displacement for several meters. Next slide, please. So we try to simulate the sliding condition along an inclined surface similar to the slope of the submassif. And so the acceleration we have here, 0.8 meters per square second, was the minimum acceleration we could apply to our rotary column. And so this is giving us a 30 degree slope, which is a overestimation of the current slope of the submassif. Next slide, please. Then we run some experiment at room humidity, but also at high vacuum conditions, so to simulate the absence of a lunar atmosphere. We then apply different normal stresses, 2, 5, 10 MPa, which then correspond to different thicknesses of a slide with a made of a material with density that we have chosen. And so the minimum thickness here is 500 meter, which again I strongly suspect is a overestimation of the initial thickness of the material that came down from the submassif. But again, it's really difficult to tell because we don't really have a clear headscarp, so it's difficult to constrain the initial volume and initial thickness of the light mantle landslide. But we couldn't choose a lower normal stress, again, for reason linked to the to Shiva, to the rotary apparatus. Anyway, we apply our acceleration until we reach a peak velocity of 1 meter per second, and then we kept the velocity constant for a sleep that ranging from 2 to 5 meters. Next slide, please. And these are our results. So left-hand side, room humidity result, right-hand side, high vacuum result. And on the vertical axis, we have the coefficient of friction. And what we see here is that we have a small reduction of the coefficient of friction, which is actually happening only at the higher normal stresses applied. And so we conclude that the unorthogonal bearing material has a high dynamic shear strength. This is also somehow interesting. Next slide, please. Because at the experimental condition we have used, in some other material, we see a significant reduction of friction. So there is a difference between materials, and the unorthogonal bearing apparently has a higher strength. And next slide, please. So we also made some microstructural observations. So we took fragments of the sample after running the experiment, made thin section, and then we observed with the scanning electron microscope. And so here on the right-hand side panel, the slip zone is at the top of the figure. And so moving down, we move away from the slip zone. And we distinguish we identify 3 distinctive microstructural zones, and each containing or not some type of class fabric. And so close to the slip zone, we see a strain localization, and then moving away from the slip zone, we end up basically having finding ourselves with starting with something that looks like the starting matrix with angular clasp. So there are 2 let's say class fabrics we kind of identified. One we called melt balls, and glass cortex aggregate. Next slide, please. And so we can look at this class fabric in a bit more detail. So MB stands for melt ball, which is here inside the red box. And below it, we have a zoom in into this melt ball. So melt ball class aggregates with solidified melt. Whereas the CCA, class cortex aggregates, are made of a central cluster and surrounded by fine-grained fragments that derive by the breaking of the cluster itself. And we have some other example here at the bottom left. We see the CCA marked grain. We see some fracture. These were, let's say, incipient fraction. Which then, if the displacement continued, it would have led to further fragmentation of the cluster. Next slide, please. Okay, so, well, we generated these microstructures, this class fabric, when trying to simulate a lunar landslide. And so we thought, okay, what if we can maybe look for or maybe observe similar class fabric in the core sample 73001 and 002. Obviously, we need to make some. We need to bear in mind different things. First of all, the microstructures that we created with our friction experiment originated close to the slip zone. So in a landslide context, that would correspond to a zone very close to the basal surface, whereas the core sample represent the top 60 centimeters of the landslide deposit, which is estimated to be at least several meters thick. So in a way, probably also doesn't even represent the entire landslide deposit. Plus, we are seeing that the sample may not yield pristine structures anymore. But anyway, apart from this negative thought, we were thinking, okay, that would be interesting if we can actually see some of the microstructures that we created in our friction experiment, because that would give us
2 minutes.
Cool. Because then it will give us important information about the mechanical behavior and the emplacement mechanism of the light mantle landslide, because then it would mean that classed fabric that were formed at the base of the slide were able to be transported right to the top of the landslide, and so possibly involving some type of turbulent mechanism. Next slide, please, which I are the conclusion. So just to summarize, from our experiment, so our experiment do not support evidence for the occurrence of friction weakening mechanism in lunar analog material. And so we somehow conclude that this type of friction weakening mechanism did not take place during the initiation of the light mantle landslide. And so this means that we need to consider other mechanisms that must have then dominated the landslide emplacement, and so responsible for the excessive runout distance of the light mantle landslide. And that's all. Yeah, that's all for me. Thank you so much.